Okay, so we're going to look at the problem that reads, a mountain climber encounters a crevasse, which is like a giant crack, in an ice field. The opposite side of the crevasse is 2.75 meters lower and is separated horizontally by a distance of 4.1 meters. To cross the crevasse, the climber gets a running start and runs purely horizontally off. What minimum speed is necessary for the climber to safely cross? Okay, so following our sort of process of motion of kinematics, we want to identify our object. So that is the climber. All right, so same ideas we've always been doing. What defines what we're interested in starting the motion? What defines the end of the motion? So we're interested in as he goes off the higher side of the crevasse and ends at the lower side. So goes off the edge and ends at the lower side where he lands. Okay, so we've kind of started talking about some additional conceptual questions to answer. Is my acceleration steady throughout this motion? Yeah, he's in free fall. Ooh, there's another one. He's in free fall. So we can write that down. So my acceleration is steady throughout the entire motion. And that's the acceleration vertically. We know that to be a value. Might not be given, but it's implied. We're only dealing with one object. And we're dealing with two-dimensional motion. All right, so he's moving both horizontally and vertically as he travels through the air. Okay, so let's draw a picture. So there's the crevasse. And when we're dealing with two-dimensional motion, remember, our work sort of doubles. So we need to set a vertical position equal to 0. And I'm going to set that at the top of the ledge. So everything above this is going to be positive vertically. Everything below that will be negative. And then we also need to set a horizontal position 0. I'm going to set it at this point where everything on this side to the right is positive and everything to the left is negative. Okay, so now we make our list of known values for both our horizontal and our vertical direction. So we have x initial horizontal, x final horizontal, v initial horizontal, v final horizontal, acceleration horizontal, and our time. And I don't need to put horizontal or vertical in our time. Remember, for two-dimensional motion, the times are always the same. The object's moving during the same amount of time. It's just one object. Okay, so then we have x initial vertical, x final vertical, v initial vertical, v final vertical, acceleration vertical, and time. All right, so let's put our values and conceptualize the problem into our list. So we start x initial. Well, our person's starting at this location in space horizontally, so 0 meters. They're going to end across the way, and we're told that's 4.1 meters across. We don't know the initial velocity, don't know the final velocity. We do know that they are the same, and in two-dimensional motion, our acceleration horizontally is equal to 0. And we don't know the time. All right, vertically, well, he's starting at the top, so he starts at 0 meters. We know that it's lower by 2.75. We're going to remember that that value is negative because it's below the 0 mark. We're jumping purely horizontally, so we know our initial vertical velocity is 0. We don't know our final vertical velocity. And because we're in free fall, we're accelerating at the rate of g. Okay, so what are we interested in solving for? Well, it's asking what speed is necessary for him to make it off the cliff. Well, that's when he goes off the edge, that's his initial. He's only moving horizontally initially. And of course, horizontal and vertical are the same, horizontal, initial, and final are the same. So we're interested in that, either initial velocity or final velocity. So V initial, X initial X final is equal to X initial plus V initial t plus 1/2 a t squared is the equation I'm going to use because I have a non-accelerating system. So this term is going to go to 0, and I end up with X final, 4.1, is equal to 0, plus V initial, which is what I want, we call that VH, times t. So 4.1 equals V sub h times t. I need t. Well, we know because we're in a situation where the object is moving the same vertically as it is horizontally, that time is the same in both. So I can go after time, recognizing that I can get that from my vertical dimension. So using the same relationship, as I have the information in there that I need, I get negative 2.75 equals 0, plus 0 times t plus 1/2 negative 9.8 t squared. Get minus 2.75 equals minus 4.9 t squared. And we get time is equal to 0.75 seconds. So now I can plug that back in to our relationship up here. I get 4.1 equals V sub h times 0.75, and my initial velocity to clear the crevasse has to equal 5.47 meters per second. All right, so recognizing that we have one object, two motions, doubles our work, two origins, two lists, relating those lists typically by time, not always, but typically by time, and then using that information to solve for what we need. All right, so this is two-dimensional motion off in a horizontal. Good job.